Okay, next lesson is lesson number 7, LR parsing and parser generators. LR1 and LR parsing. We've seen that the following grammar is an LR0 grammar, and we constructed the corresponding LR0 states, which define a shift-reduce parser. So it's LR0 because it has no look-ahead symbol, so I'm guessing LR1 is a 1 look-ahead symbol. What instead of the production S tends to S plus E, the grammar included the production S tends to E plus S. Then the construction of the LR automaton would have proceeded a little differently. In particular, consider what happens when the parser completes an E from the initial state. So, initial state here, we have to shift or predict S, which gives us E plus S and E. Then we have to predict E, which gives us a number or S within parentheses. So if we ended up at some point down the line completing one of, both of these E's, we would end up in this state where we have E dot plus S, S tends to E dot. So because we finished this, we would expect to reduce. But we haven't finished this top one. We can always see a problem with this automaton because it's not always clear what to do in state 3. The parser is ready to reduce the production S to E, but if the next input token is a plus symbol, the parser could also shift that token to go to a new state. The right choice turns out to be to shift when the token is plus symbol and reduce otherwise. But nothing in the LR0 construction we've seen so far takes the look-ahead token into account. Notice that an early parser would simply try both the scan and complete actions, and one of them would get stuck based on the next input symbol. Yep. But the LR parser has to commit to one of them. So an LR1 parser uses the look-ahead to decide which action to take. Okay. This observation leads us to extend the LR automaton construction to an LR1 automaton. Just as in the LR0 automaton, the states are a set of items that is closed under prediction. Yep. However, I'm still trying to understand what closed under prediction means. I'm guessing it's the states are a set of items that is closed under prediction. So I'm guessing it just means that we predict until we can't predict anymore. So here, this isn't closed under prediction because we need to predict the S. We have S remaining. Then we have an E remaining. And then finally we get to a state where E tends to terminals. So I'm guessing that that just means now it's closed under prediction. Guessing, yeah, that has to be what it means. Notice that an early just as the LR0 automaton, the states are a set of items that is closed under prediction. However, the items now contain a set of look-ahead tokens. Lambda? Is that a lambda symbol? Yep. Lambda. Thus, an LR1 item has the form x tends to alpha dot beta, and then we just have lambda off here to the side. So we have the look-ahead token off here to the side. Whereas before, the symbols alpha represent the top of the automaton stack, the dot represents the current input position, the symbols beta derive possible future input, and the set of tokens lambda describes tokens that could appear in the input stream after the derivation of beta, and not, as one might think, the tokens that might follow the dot. Okay. To build an LR1 automaton, the initial state is the closure of the item. S prime tends to dot S and then the end of input symbol, and the look ahead is nothing. Each automaton transition is done as in the LR0 construction, except that the look ahead set is propagated to the next state and the closure is taken as just described. With the LR1 construction process, the two states we built earlier look similar but include look ahead information. Okay, so the first one, S prime tends to S and then the end of input. There's no look ahead. Yeah, because there's no, you can't look at anything after the end of input symbol, I'm guessing. Then S, we predict S, and that becomes E plus S, with the end of input symbol being the look ahead, because symbols, the token, so lambda describes tokens that could appear in the input stream after the derivation of beta. So after we derive all of this, we could potentially see, so the only, describes tokens that could appear in the input stream after the derivation of beta, and not, as one might think, the tokens that might follow the dot. So if we have E plus S, the only thing that could follow that is the end of input symbol. I'm guessing that's what it's trying to say. Yeah, so down here, if we see a number, the the things that could follow it are the end of input symbol or a plus symbol. Pretty sure that's what it's getting at. So with the LR1 construction process, the two states we built earlier look similar but include look ahead information. So if we're in this state and we complete an E, or we've taken E, we would see we could complete E here. A look ahead would be the end of input, but we can also have we could also continue scanning this plus symbol, with the look ahead being the the end of input symbol. Why is the end of input symbol there? I'm confused because let's keep reading. With this extended automaton, the ambiguity about what to do in state 3 is removed. The production S tends to E should only be reduced if the look ahead token is the end of input symbol. Okay. If the look ahead token is a plus, then the parser should shift the token, and any other look ahead token indicates a syntax error. So in this case, the look ahead symbol is the end of input, therefore we should reduce on this state. A grammar is LR1 if the action for each of its states is unambiguous. All the complete items on which a reduction could be done have disjoint look-ahead sets. And further, those look-ahead sets do not include any token C for which the state contains an item of the form x tends to alpha, some constant beta. Okay, so when these conditions hold, only one action can appear in each entry of the parser action table. Trying to decipher that. So grammar is LR1 if the action of each of its states is unambiguous. All of the complete items on which a reduction could be done have disjoint look-ahead sets. And further, those look-ahead sets do not include any token C for which the state contains an item of the form. Well, okay, yeah, because if you have, I'm guessing what it's saying is if any of the sets, the look-ahead sets contain, yes, if any of the look-ahead sets contain a token C, and we still have an item where we can scan in a C, then what basically not done. We should scan in the C and create, like, continue parsing, create new states, whatever. I think that's what it's trying to say. When these conditions hold, only one action can appear in each entry of the parser action table. Conflicts. When a grammar is not LR1, it is because some entry in the action table cannot be assigned a single action. There are two ways that things can go wrong. First, there could be two completed items of the form x tends to some symbol. First, there could be two completed items of the form x tends to some completed terminal, and x prime tends to some terminal prime, and lambda prime, whose look-ahead tokens lambda and lambda prime both include some token C. In this case, we say that the grammar has a reduce conflict on C. The second way to fail to be LR is to have a shift reduce conflict in some state. In this case, the state contains a completed item of the form x tends to some terminal completed, but also an incomplete item of form y tends to alpha dot some constant beta, where we have C is in the set of look-ahead tokens. If the look-ahead token is C, the parser doesn't know whether to shift C or to reduce. Much of the challenge when using a parser generator that does not generate counterexamples automatically is to identify the grammar issues that lead to reduce or shift reduce conflicts. Ambiguous grammars often lead to a surprisingly large number of conflicts. So it is prudent to build up grammars incrementally, testing them for conflicts as you go. Okay. All right. Definitely going to run into these at some point, I'm sure, when doing the assignment or in the homework. So I'm going to keep reading. Precedence declarations. Bottom-up parser generators usually support precedence declarations as a way to resolve conflicts. Precedence declarations do not fundamentally increase the power of the parser, but often make it easier to write grammars for programming languages. For example, suppose our example grammar contained the production E tends to E plus E. This grammar is ambiguous with respect to associativity. So the LR1 construction produces a state with a shift-reduce conflict on the token plus. This is the kind of state we would expect the parser to get into if it handled input like 1 plus 2 dot plus 3, where the dot marks the current input position. So, okay. So we've finished this, but we also still have more to go. The syntax for precedence declaration varies, but in CUP, for example, we can write a precedence declaration, precedence left plus, to cause the parser to choose the reduce action when the look ahead token is plus, resulting in left associativity. Conversely, we can write precedence right plus to cause the parser to choose the shift action, resulting in right associativity. Okay, so we can just tell it. We can just tell it to reduce here, or we can tell it to shift. We can also get shift-reduce conflicts arising from precedence. For example, suppose our grammar contains the two productions, E tends to E plus E, or E times E. In this case, we'll get states with shift-reduce conflicts like the following, corresponding to input like 1 times 2 plus 3 and 1 plus 2 times 3. Yeah, okay. So yeah, it's a problem because we don't know whether we should be reducing here or whether we should be shifting. The left state has a shift-reduce conflict on token plus, and the right state has one on token asterisk. These conflicts are easy to resolve using precedence declarations, however. In CUP, the order of precedence declarations defines precedence of different tokens. For example, these declarations would make times have higher precedence than plus. Precedence left plus, precedence left times. Operationally, these declarations would cause the parser to reduce the left state on token plus. So reduce when we see a plus token, and to shift the right state on token asterisk, achieving the desired precedence. LA-LR parser generators also allow a precedence declaration to be attached directly to a production to specify its priority with respect to other productions of the same non-terminal. Such declarations are helpful when the production does not itself use the token whose precedence is being used. LA-LR grammars. The number of LR1 states is often unnecessarily large because the LR1 automaton ends up with many states that are identical other than look-ahead tokens. This insight leads to LA-LR automata. An LA-LR automaton is exactly the same as LR1 automaton except that it merges together all states that are identical other than look-aheads. So it merges all states together other than look-aheads. it merges all states that are identical other than lookaheads. In the merge, the lookahead sets are combined for each item. The LALR automaton can be constructed directly. Of course, it's not necessary to build the full LA1 automaton and then merge. Many parser generators are based on LALR, including commonly used software like Yak, Bison, Cup, ML Yak, Camel Yak, and many here. While LALR is in practice just about as good as full LR, it does occasionally lose some expressive power. To see why, consider what happens when two LR1 states in the following diagram are merged to form the state marked M. Ascends to N. So we merged the states, and you get conflicting, what's the word? I can't remember the word, but they're conflicting look-ahead sets. The two states on the top are unambiguous LR1 states, in which the look-ahead character indicates which of the two productions to reduce. But when merged, the resulting state has reduce conflicts on both plus and the end of import symbol. When merging LR1 states creates a new conflict, the grammar must be LR1 but not LALR1. Okay, so to be LALR1, we can't have any reduce conflicts or shift reduce conflicts. Okay. Comparing the power of different parsers. Early parsers are the most powerful parsers we've seen. They can recognize any grammar, including ambiguous grammars. They can even recognize ambiguous languages, languages for which there is no unambiguous grammar, such as the union of M and N. Not sure what that represents. Early parsers expose the full power of the non-deterministic pushdown automaton, NPDA, non-deterministic pushdown automaton, which you can think of as a shift-reduce parser with an oracle telling it what to do in case of conflicts. Okay. Because I mean, it's an oracle in the sense that it tries out everything and then just determines the right one. LR1 parsers, on the other hand, expose the full power of the shift-reduce parser, push-down automaton, or PDA. Anything that can be recognized by a shift-reduce parser with one token look-ahead is LR1. For any K, LRK is strictly more powerful than LLK. However, LALR1 is actually incomparable to LL1, though in practice it is more expressive. However, there are still unambiguous grammars that cannot be parsed by LRK parsers for any K, such as grammar for a language of palindromes. These comparisons are depicted in the following diagram. So LALR can't be directly compared with LL1 nor LLK. LR1, the push-down automaton, is more powerful than LALR1. then LRK is more powerful than those, and it can parse anything that LLK can parse. Then unambiguous grammars. So LRK cannot parse all unambiguous grammars, but early non-deterministic pushdown automaton can parse everything. It's pretty cool. Sweet. So that was a pretty short lesson. What did I not understand? I guess the conflicts is the main thing that I didn't understand. So conflicts here. I guess this is a shift reduce conflict because you don't know whether to shift or to reduce. So in this case, in the top case, you would want to reduce. Then here you would want to shift. We can also get shift reduce conflicts arising from precedents. For example, suppose our grammar contains two productions. In this case, we'll get states with shift reduce conflicts like the following, corresponding to input like 1 times 2 plus 3. So when you specify precedents, that gets rid of shift reduce conflicts specifically for things like this, arithmetic, things like this. The right state has one on token. Yep, these conflicts are easy to resolve using precedence declarations, however. In CUP, the order of precedence declarations define precedence over different tokens. Operationally, these declarations would cause the parser to reduce the left state on token plus. Okay. Because the look ahead symbol is plus, we decide to reduce, is that right? To reduce. Okay, so if the look ahead symbol here is plus, wait, why wouldn't you scan? If the look ahead symbol is plus, why wouldn't you just scan? Unless, okay, so the look ahead symbol determines, if the look ahead symbol matches, then you reduce. I've already forgotten. But so here, there is no plus, therefore we shift. Okay, so that makes, yeah, okay. So by reducing on a plus symbol here, we complete the E non-terminal, and then by shifting on the times symbol here, we make times have a higher precedence than plus. Okay, that makes sense. LO1 construction is fine. Conflicts, I still don't really understand this this notation. When a grammar is not LR1 is because some entry in the action table cannot be assigned a single action. There are two ways that things can go wrong. First, there could be two completed items of the form x tends to some completed terminal and x prime tends to some other completed terminal and some other look-ahead token. These look-ahead tokens both include some token C. In this case, we say that the grammar has a reduce conflict on C. I don't understand. I would need to see an example of a reduce conflict. Let's see if ChatGPT can spin one up. Show me an example of a reduce conflict on an LR1 grammar. Reduce conflict occurs when the parser encounters a state where it has two or more possible reductions for the current look-ahead symbol. This typically happens when there are two or more production rules with the same look-ahead symbol in the same state. Here's a simplified example. Consider the following LR1 grammar. Yep, okay. And the LR1 items for this grammar. Yep. So the look-ahead symbol is the end of input symbol here. The look-ahead symbol for this B is how do you derive the look-ahead symbol again? Symbols beta derive possible future input, and the set of tokens lambda describes tokens that could appear in the input stream after the derivation of B, and not the tokens that might follow the dot. Describes that tokens that could appear in the input stream after the derivation of beta. This is ChatGPT. I have no idea if it's correct, but can C occur in the input stream? Sorry, can A occur in the input stream after big A? I have no idea. Continue. Now let's construct the LR1 parsing table. In the state where the look-ahead symbol is C, we have the following transitions. So we've completed B. B is C. B tends to dot C. Shift to state 5. That makes sense. So we shift over here. Reduce using B to C. but in state 3 there is a reduce conflict because the parser has two possible reductions for the look ahead symbol C. Oh, okay. Gotcha. So A can shift to C and B can shift to C, so the parser won't know. Yeah, the parser can't tell which one to shift to reduce. Sorry. It can either reduce the production S to B for the production rule B to C. This. Wait, what? It can either reduce using the production rule S tends to BB, or the production rule B to C. The ambiguity in choosing the correct reduction leads to a reduce conflict. In practice, resolving reduce conflicts involves restructuring the grammar to eliminate ambiguity. This can include left factoring, reordering rules, or introducing additional non-terminals. I'm still a bit confused. So could be two completed items of the form like this, whose lookahead tokens, this and lambda and lambda prime both include some token C. In this case, we say that the grammar has a reduce conflict. Oops. Can I get a simpler example? Yeah, all right, let's break it down. All right, so we have X. So we're in some state where we have S tends to X dot A and X tends to B, but X can also tend to C. In this LR1 grammar, we have three items in a state where the lookahead symbol is A. The lookahead symbol is A because A can occur after X. The dots indicate the position of the input cursor. Yep. Now let's look at the LR1 parsing table for the state with A as the lookahead symbol. So this makes sense. So we want to get to, if we encounter a B, we shift to state 2. If we encounter a C, we shift to state 3. In state 1, in state 1, there is a reduce conflict because there are two possible reductions for the look-ahead symbol A. The parser can either reduce using the production rule X tends to B, why is this saying shifting? Don't we want to reduce, not shift? We want to read it in, so I guess that's shifting. Reduce using the production rule. X tends to B or X tends to C. This ambiguity in choosing the correct reduction leads to reduce conflict. To solve such conflicts, you will need to modify the grammar to make it more suitable for LR parsing. Okay. Alright. So it's when a non-terminal can tend towards multiple different terminals, I guess, with the same lookup token, look ahead token. Okay. All right. We're slowly making our way through this pilot course. Hopefully things go faster after this. But it's been difficult, and I'm slowly picking up this stuff. I'm gonna go watch a YouTube video after this, which I find really helps when you see someone walking through the algorithm. It helps a lot to understand it. So yeah, thanks for watching, and I'll see you in the next video.